Now that we've spent the last few months studying triangles, we're going to turn our attention to quadrilaterals. And quadrilaterals, by definition, are four-sided polygons. So they have four sides rather than three. And the one property of significance for all quadrilaterals is that the sum of their angles is 360 degrees. And within the world of quadrilaterals, there are specific types. There are kites, there are parallelograms, and there are trapezoids. And then within the world of parallelograms, there are rectangles and rhombuses, and also squares. And in the world of trapezoids, there are isosceles trapezoids. And when you look at this diagram as a whole, what I want you to appreciate is that as you work your way from the top towards the bottom of the diagram, each of the different groups inherits properties of the groups above them. So for example, a square has all the properties of a rectangle and a rhombus, and it also has all the properties of a parallelogram, and it has all the properties of a quadrilateral. So in a sense, these different shapes inherit the properties of the ones above them. And what I plan to do over the next few minutes in this video is look at each of the big groups and talk more specifically about their definitions and their properties. Let's take a few minutes now to look at kites. And the definition of a kite is a quadrilateral with two distinct pairs of consecutive sides that are congruent. So I'll go ahead and mark on the picture of this kite. This side is congruent to that side, and this side is congruent to that side. And a result of that definition, several things are also true about a kite. First off, one pair of opposite angles are congruent. This angle up here is congruent to that angle down there. And we can see why by adding to this picture a diagonal. So I'm going to construct a diagonal across this kite. And we've broken the kite now into two triangles. And these two triangles are congruent to each other by SSS. And as a result of that being true, then we can mark this angle up here as being congruent to that angle down there by CPCTC. So one pair of opposite angles are congruent. Also, these two angles over here are congruent to each other, and these two angles over here are congruent to each other by CPCTC. So that diagonal is bisecting the other two angles. And then finally we can do one more thing. I'm going to go ahead and draw the other diagonal on the diagram. So it's going to start up here and cut all the way down to there. And what you might notice is that these two diagonals appear to be perpendicular to each other, and the diagonal I just drew appears to be bisected. And both those things are in fact true, and here's why. If we look at this triangle right here, and we look at that triangle right there, they are congruent by SAS. And as a result, we know then that this segment right here is congruent to that segment by CPCTC. So that vertical diagonal has indeed been bisected. Also, because these two angles are congruent here by CPCTC, they must both be 90 degrees. So I can go ahead and mark them as 90-degree angles. So what we've just seen is that that same long diagonal that goes horizontally is the perpendicular bisector of the other diagonal. Let's now turn our attention to parallelograms. And parallelograms are quadrilaterals whose opposite sides are parallel. So this side is parallel to that side, and then this side is parallel to that side. And as a result of that definition, the first thing to note is that consecutive angles are supplementary. So these two angles have to add up to 180, and that's because these lines are parallel and these are same side interior. And also this angle is supplementary with that angle, again because those lines are parallel and they are same side interior. So consecutive angles are supplementary. In addition to that, opposite angles are congruent. Because these two angles add up to 180 and those two angles add up to 180, then this angle and that angle must be congruent to each other. And in similar fashion, these opposite angles here and here must be congruent to each other. A third property of parallelograms is that opposite sides are congruent. And to see that, it helps to have one diagonal drawn. So I'm going to go ahead and introduce a diagonal into this diagram. I'm going to draw one that goes from here to there. And that diagonal breaks this parallelogram into two congruent triangles. And these two triangles are congruent because we know that this angle right here is congruent to that angle right there. We know that this angle right here is congruent to that angle right there because these sides are parallel, and that transversal creates alternate interior angles that are congruent. So by AAS, these two triangles are congruent to each other. And because they're congruent to each other, that means that this side is congruent to that side by CPCTC, and this side is congruent to that side by CPCTC. To demonstrate the final property of parallelograms, I'm going to go ahead and delete these markings I created. And what I'm going to do is put on the diagram the other diagonal. So it starts down here and works its way all the way across to there. And what you might sense is that each of these diagonals has been bisected by the other one. In other words, each diagonal cuts the other into two equal parts. And you can see why that happens by, again, using congruent triangles. In this picture, we know that this side is congruent to that side, and we also know that this angle is congruent to that angle, and this angle is congruent to that angle. So therefore, these two triangles are congruent by ASA. And because these two triangles are congruent, what that means is that this segment is congruent to that segment, and then this segment here is congruent to that segment there. So you can see that indeed both triangles have been bisected. You also might notice that these two triangles are congruent to each other by rotation. If you rotate this 180 degrees, it will land on top of that one, which makes these two segments match up and those two segments match up. Let's next turn our attention to rectangles. And rectangles are a special type of parallelogram, so they inherit all the properties of a parallelogram that we just went over. But in addition to that, the definition of a rectangle is that it's a parallelogram with four congruent angles. So I'm going to go ahead and mark the four angles, and because they all add up to 360 and they're congruent, each of them must be 90 degrees. So I'm going to go ahead and mark them all as having 90 degrees. And one interesting result of that is that in all rectangles, the diagonals are congruent to each other. And I'll go ahead and draw them, the two diagonals now. The first one goes from the lower left to the upper right, and then the second one goes from the upper left to the lower right. And those two diagonals are congruent to each other. And that might make some intuitive sense. If you've ever been on a basketball court and had to run diagonally across the court, it doesn't make a difference if you go from the lower left to the upper right or the upper left to the lower right. It'll cover the same distance. And here's a proof of that. First of all, we already know from the fact that a rectangle is a type of parallelogram that this segment is congruent to that segment. So if we look at this triangle that overlaps with that triangle, they both have these segments congruent, they share this segment across the bottom, and they both have a right angle. So by SAS, this triangle and that triangle are congruent. So therefore, these corresponding parts, this long length here and that long length there, are congruent to each other. A rhombus is another type of parallelogram. So it has all the properties that a parallelogram has, but in addition, it has four congruent sides. So I'm going to mark these four sides as being congruent. This side, this side, and that side are all congruent. Two properties result from this. The first is that the diagonals in a rhombus are angle bisectors, and the diagonals are also perpendicular. So I'm going to go ahead and place the diagonals on the diagram. So there's one diagonal, and here is the other diagonal. And those two diagonals are angle bisectors, and also the diagonals are perpendicular to each other. And here's the reason why. First of all, we know that the diagonals are bisected, so I'm going to mark these two segments as being congruent to each other. And also, these segments are congruent to each other. So as a result, you might notice that all four of these triangles are congruent to one another by SSS. So as a result, these four angles that are all corresponding must all be 90. And also, these two angles right here, which correspond to each other, must be congruent. And these two angles must be congruent, etc., etc. Finally, let's look briefly at a square. And a square is not only a rhombus, it's also a rectangle. And it's also a parallelogram. So it inherits all the properties that a parallelogram has, and a rectangle has, and a rhombus has. And the definition of a square is just a polygon with four congruent sides and four congruent angles. So the properties exhibited over here with a rectangle, that the diagonals are congruent, and also the properties of a rhombus, that the diagonals bisect angles and that they are perpendicular to each other, hold true for a square. Next, let's turn our attention to trapezoids. And a trapezoid is a type of quadrilateral where exactly one set of sides are parallel, and those are known as the bases. So in this diagram, the parallel sides, or the bases, are this one here and that one there. And one property that results from that is that some consecutive angles are supplementary. These two angles are supplementary because they are same side interior to these parallel lines. And also these two angles are supplementary because they are same side interior of those parallel lines. And within the world of trapezoids, there are also isosceles trapezoids. And what makes a trapezoid isosceles is if the other two sides, those that are not parallel, these over here, happen to be congruent. And they are called the legs. So I'm going to go ahead and mark this segment as being congruent to that segment. And as a result of that, these two angles down here, these base angles, are congruent to each other, and these two angles up here are congruent to each other. In addition to that, the two diagonals in an isosceles trapezoid are congruent to each other. So if I were to draw them in here, which I'll go ahead and do, there's one, and there's the other. You'll notice that they are congruent to each other, which we can show with congruent triangles, but also notice that they do not bisect each other. This segment right here, this diagonal, has a longer part and a shorter part, so it's not bisected. And similarly, this long segment, this diagonal, has a long segment and a short segment. So looking back on this diagram as a whole once again, what I'm hoping you'll appreciate is that these various quadrilaterals inherit properties of those that are linked above it. So a square has all the properties of a rectangle and a rhombus, which also have all the properties of a parallelogram, which have the properties of a quadrilateral. Likewise, an isosceles trapezoid has all the properties of a trapezoid and a quadrilateral. And a kite has all the properties of a quadrilateral. And I have one message down here that I want to highlight, and my advice to you is not to try to memorize these properties. As long as you can draw a reasonably accurate sketch, then you can use congruent triangles in CP/CTC to show these properties are true. So don't feel compelled to memorize this chart, rather try to understand it. Finally, here's a more visual way to make the connection among the various types of quadrilaterals. First of all, in the world of quadrilaterals, you can have all sorts of four-sided shapes, and any shape that doesn't fall into one of the more specific categories would sit out here in this part of the diagram. But within the world of quadrilaterals, there is a smaller world, or a smaller group, that are kites, and those are four-sided shapes where two consecutive pairs of sides are congruent. And then also there's a world of rectangles, which you're familiar with, a world of rhombuses or rhombi, and those worlds overlap, and where they overlap we have squares, and squares are not only rectangles, but they are also rhombi. And then finally there's another world of trapezoids, and these are quadrilaterals that have only one set of parallel sides, and they're called the bases. And then if the legs are also congruent, in addition to being trapezoids, those are isosceles trapezoids. And this visual should give you sort of a sense of the relative positioning of the various types of quadrilaterals and what properties they inherit.